Hello and welcome friends. In the past couple of lectures we have been discussing backtracking, which is one of the algorithmic techniques to solve a certain class of computational problems. Now today we will be discussing another example where backtracking can be used to find an optimal solution. Now this problem at hand is, as you can see on the screen, the knapsack problem. Now you have already tried to solve a variant of the problem that we will be discussing today. You have already solved the fractional knapsack problem using a greedy method earlier. Now today we will be discussing the 0-1 knapsack optimization problem. Now as you can get from the title there, the 0-1 knapsack optimization problem is similar to its counterpart as you have tried to solve using the greedy method. The only difference here is that an item can be included in the solution either as a whole or not at all. So we cannot take fractional values of any particular item's weight in this particular problem, the 0-1 knapsack problem. So this current problem is a little bit different than what you have already tried to solve using the greedy method, although we will be using the similar idea as was used in the greedy method to solve the fractional knapsack problem later. It will be clear in a couple of moments. So what is this 0-1 optimization problem? Basically it's similar to the earlier case, as you can see on the screen. We are given a set of positive weights, n positive weights, W1, W2, so on up to n. Similarly, n positive profits which are associated with these weights. So we have n items, each item has an associated weight and a profit. We are also given a positive number m. Now this m is given as the capacity of the knapsack. So our problem here is that we are given a knapsack of a certain capacity m, and we are asked to select items from the given set. Each item has a specific weight and an associated profit with it. So our objective is to fill the knapsack to its capacity. Okay, maybe we can fill a little less, but not more than the capacity. And our objective is to maximize the final profit. And the constraint here is, which is different than the fractional knapsack, that an item can either be taken as a whole or not at all. Okay, so we cannot take fractions in this case. So as you can see on the screen, this problem is simply generalized by specifying that the summation of wi xi for I equal to 1 to n should be less than or equal to m. This m here is our capacity of the knapsack. This wi is the weight of item I, and this xi is basically how we provide the solution. In our earlier examples using backtracking, I have specified that we'll be using fixed tuple solution. So this xi in our case here can either be 0 or 1. If it is 1, then the weight of that I or that ith item is considered or added to the knapsack. If it is 0, then it is not considered. So our objective here is that whatever items we select or put in our knapsack, the total weight of the items that we add to our knapsack should be less than or equal to the capacity of the knapsack. That is this part basically specifies that. In addition to filling the knapsack, our objective is to maximize the profit gained by filling the knapsack with the specific items that we have selected. So as I said, that pi is a profit associated with an item I. So we add the profits of all the items that have been considered or that have been put into the knapsack, and our objective is to find such a solution of xi's such that the total weight is less than or equal to the capacity of the knapsack, and the total profit obtained thus is maximized. So it is the maximum profit that can be obtained from the given set. So as an example on the screen, as you can see, we have a total of 4 items, and each of these items has an associated weight wi here. So w1 is 2, w2 is 3, w3 is 4, and w4 is 5. And in addition to these weights, we have certain profits associated with these items. So item 1 has a profit of 3, item 2 has a profit of 6, item 3 has a profit of 9, and item 4 has a profit of 14. In addition to these, so this will be the input of the problem, weights and associated profits of the items. We will also be given capacity of the knapsack. So in this example, for the sake of an illustration, we have taken m, that is the weight of the capacity of the knapsack, to be equal to 8. And one of the ways of specifying a solution to this problem is by our solution vector, which we have specified as xi. So x1 is equal to 1 here means that we are considering or putting this weight 2 in our knapsack. and the profit that needs to be considered for our maximization problem is 3. Similarly, we are x2 here is also 1, so it means the second item is also added to the knapsack, and we have to consider both the weight and the profit of this particular item. Similarly, item number 3 is x3, in this case is 0, so the third item is not considered. Similarly, the fourth item is not considered at all. From this we can see that the total weight that has been filled in the knapsack is weight of 1, which is 2, plus weight of 2, which is 3, or item number 2, which is 3. So 3 plus 2, which is 5. So 5 is less than 8, which was the capacity of the knapsack here, as we have specified. So this is a possible solution to the current problem, because this condition is satisfied. So the sum of the weights of all the items that are considered for the solution is less than or equal to m. In this case, it is equal to 5. However, we are not very sure whether profit is maximized or not, because the total profit gained in this case, in this solution, by this solution vector here, is 6 plus 3, which is equal to 9. So we are not very sure right now whether there is another solution vector which whose weight will be less than or equal to m and whose profit is greater than 9. We'll see that later how we obtain that. Similarly, we have another solution vector. A possible solution vector is, we are not considering item number 1, we are considering item number 2, 3, and 4 is also not considered. So in this case, again, weight constraint that is satisfied. However, we are not sure about this particular maximization, because in this case the profit is 9 plus 6, which is 15, and the total weight here is 7. So at least this solution is better than the earlier one. Another vector here in which we consider item number 1 added to the knapsack and number 2, item number 3 are added to the knapsack. However, this solution vector is not feasible, as the total weight of all these items, if we add to the knapsack, is 7 plus 2 is equal to 9, which is greater than the capacity of the knapsack. So this solution vector here is not a feasible solution to our problem, 0 knapsack problem. Similarly, the last example here, this solution vector, which considers only the second and the fourth items to be added to the knapsack, is the optimal solution to this particular problem, because the weight added to the knapsack is equal to the capacity of the knapsack, which is 8, 5 plus 3 in this case, and the profit is 20. If you analyze this particular problem, you will see that the 20 here is, which is 14 plus 6, is the maximum profit that can be obtained from this particular problem. We'll see how we will use backtracking to get to this solution in a couple of moments, but this is just an idea of what the 0 knapsack optimization problem basically is and what our objectives are. Now, in order to devise a solution to this 0 knapsack problem using backtracking, the important assumption that we are making is that the order in which we consider our profits and weights, for example, each item has a profit and a weight associated with it. So it's important that we order our items such that, if for example item number 1, item number 1's profit divided by its weight is greater than or equal to item number 2's profit divided by its weight. The relationship between, or we can say that the order in which our weights and profits are considered for each of the items, so we need to sort our items such that the associated profits and weights have this relationship. That is, in the sequence, the consecutive pair of profit and weight ratios has this relationship, that the ith ratio is greater than or equal to the I plus 1th ratio. So this is one of the important assumptions based on which we will be building our solution to the backtracking problem. So this is the assumption on which we are building our solution to the backtracking problem. So earlier slide you saw that we had arranged the profit and weights in an ascending order, but since the requirement is that the ratios have to satisfy this constraint, so whenever we are given a problem, we ensure that we sort the profit and weights of items such that this particular constraint is satisfied. So we have ordered the earlier set of profits and their associated weights such that the first item's ratio, which is the profit by weights ratio, is greater than the second item's profit and weight ratio, whose value is greater than the third item's profit and weight ratio. Similarly, its ratio is greater than the last one. So this is the assumption that we'll be considering, and we'll have to arrange our profits and weights in this particular order. Now, in our earlier examples, when we were building solutions to the backtracking problems, now we have always talked about some kind of a bounding function, which basically tries to reduce the search space of the state space tree. Now, for backtracking, the bounding function that we'll be using is, for example, if we are at any particular node in the state space tree. So, at each node, we'll try to use an upper bound on the value of the best feasible solution obtainable by expanding the given live node and any of its descendants. What this means is, whenever we reach a particular node, okay, before we start expanding it to search for all the paths that may lead to a possible solution, we'll try to find what is the best possible or the most optimal solution or the highest possible profit that we can gain if we expand this current node. Okay, so we are somehow trying to estimate the highest possible profit before we in fact expand this particular node. Okay, we try to see what is the best possible profit that can be obtained if we expand this node. Now, if that particular profit, if this upper bound value is not that we estimate from the current node before expanding it, if this value is not higher than the value of the best solution determined so far. Okay, let's suppose we have determined a couple of, by traversing or building our state space tree, if we have already determined some solutions and we have recorded the best solution so far, if at any particular node, if the upper bound that we calculate is not greater than the best solution determined so far, then this particular node, the current node for which we have computed the upper bound, can simply be killed. We will simply ignore it and we will not expand its children for finding the solution. Okay, so how do we do that? How do we find an upper bound? Is there is a requirement for this case. We basically need to relax the constraints of the 0-1 knapsack optimization problem. That is why I addressed the greedy method that you have used to solve the fractional knapsack optimization problem. Let's suppose we have already found the values of the solution vector up to index number k. So, let's suppose for k is equal to 2. So, for the first two items we have determined whether to include them in the knapsack or not. Now, for the remaining items we relax the requirement that xi needs to be either 0 or 1. We'll need to relax certain constraints that are associated with the 0-1 knapsack optimization problem. So, let's suppose we have already found the solution, or we will say a partial solution up to a particular index k. So, up to k number of items, we have determined whether an item has to be included in the knapsack or not. So, partial, for example, solution vector has been determined up to k, and we have to decide for k plus 1 to n items whether these items can be added to the knapsack or not, and what profit do we get. So, let's suppose we have already found the values of xi from 1 to k, and we need to determine for k plus 1 to n the values for the solution vector. Now, the relaxation here is that we relax the requirement for xi to be 0 or 1. So, as I earlier said, for the 0-1 knapsack problem, the solution vector's elements can either be 0 or 1. Either we include the element in our knapsack or we do not include it. However, for the 0-1 knapsack problem, for bounding our solutions or for limiting our search space, we need to relax this constraint to we allow this xi to be a fractional value between 0 and 1. For items from k plus 1 to n, only for items from k plus 1 to n. So, we consider that up to k we have determined the values of xi either 0 or 1, and for the remaining items we relax this requirement of having discrete value for xi either 0 or 1, we relax it to a fractional value. So, we allow this xi to take fractional values. Now, at this point of time, the solution can now be obtained, or not the solution, in fact, the upper bound, which is a requirement for our bounding function, can now be determined by the greedy method that you have already used for the fractional knapsack problem. We'll see how basically we use this particular concept in order to obtain our solution. An example is shown here. Let's suppose k here is 1. On the screen we can see this is, let's suppose k is equal to 1. So, first item we have determined that we have considered it to be part of the knapsack. So, we need to determine the values of x1, x2, x3 and x4, okay, whether each of these items can be added to the knapsack or not. Now, as I said, using the greedy algorithm, wherein we relax the requirement for xi to be a fractional value, using the greedy algorithm or the greedy method approach, the feasible solution from this point onwards. So, if we had considered the first item, okay, so the weight added to the knapsack would be 5, okay, how much portion of the second item can we add to the knapsack? Okay, so it is only 3 out of 4. Okay, so because our m in our earlier example, or the capacity of the knapsack we considered was 8. So the fraction of the third item is 3/4. So how much profit do we get from this? The profit is, or the upper bound, or the maximum possible profit is 14, which was the first item, then 3/4 into 9 here for the second item, and similarly, since by considering this 3/4 of the second item, the knapsack would be full, so the remaining items cannot be included in the knapsack. So this is the upper bound that can be obtained if we expand this current node. Okay, this is the best possible upper bound or best possible profit that can be gained if we consider one, or if we consider the first item. Okay, and this is the best possible profit that can be obtained if we take x1 to be equal to 1. So in a moment we will be discussing how we build our state space tree and find our final solution, but this is just an idea of how basically we compute our upper bound at any particular node. So let's try to formally use these concepts and try to solve problem at hand. So initially the profit that we can obtain is taken to be equal to -1. Okay, so the initial profit is set to -1. We do not have any solutions as of yet. The upper bound is not known at this particular moment, and as I said, the highest profit here is -1 for the time being. So whether we should expand from the current node or not will depend upon whether the upper bound obtained, the best profit obtained by expanding this node, is greater than or equal to -1. Okay, so although for the first case, for the initial node, we do not test this requirement, or we do not test the bounding function, we simply consider or build our first child of the root by taking x1 equal to 1. But for an illustration purpose, we will see whether our bounding function will help us take a decision or not. So if we consider the current node, okay, expanding the current node or computing the upper bound for this current node using the greedy method would be the first item is considered as a whole, and the second item is taken as 3/4. Okay, so the total profit is 20.75. So the upper bound, the best possible profit that can be obtained if we expand this current node is 20.75, which is way greater than the highest profit so far, because initially we take our highest profit to be equal to -1. So we will expand this node by creating the first child. We'll change the orientation a little bit. In our earlier cases, we were taking left child as the case when the item was not considered for, or xi is equal to 0. So based on this finding that the upper bound from the current node, from the root, was way greater than the highest profit so far, so we'll create our left child. So x1 is equal to 1 in this case, and the profit gained up to this point now is 14. Okay, we will save this to be as the highest profit so far. So highest profit so far for the time being is 14 in this particular case, and we have set x1 equal to 1. Now again, if we want to create the left child, meaning x2 is equal to 1, the upper bound would remain the same. In fact, for whenever we will create a left child for any particular node, it's not necessary to compute the upper bound, because the upper bound will not change. Okay, so in this example, as you can see, variable here, remembering the current weight in the knapsack, because we will have to verify whether the current weight is less than or equal to m or not. Whether it is less than m or not, only then can we continue. If it is greater than or equal to the capacity of the knapsack, then we will have to stop. So the current weight that has been added to the knapsack is 5, which is the weight of item number 1 that we just considered, and the highest profit so far is 14, which is again the profit obtained from item number 1. Now when we consider building the left child of this particular node, now, so the live node is this node here right now. So as I said, we will only be computing trying to find the upper bound when we are creating the right child. For the left child, that is when we consider the item, the upper bound does not change, so the upper bound remains the same. So in addition to that, we may also need to check if the next item that is to be added to the knapsack overfills the knapsack or not. In this case, as I said, the current weight of the knapsack is 5 at this particular point. So if we consider the left child of this particular node, the left child here means x2 is equal to 1. Now considering x2 to be equal to 1, x2 has the weight of 4. So 4 plus 5 would be 9, which would exceed the size or the capacity of the knapsack. So we cannot expand this particular node. So left child of this particular current node is killed. Okay, so it is treated as null. So we are not expanding the left child in this case. Now this here means that we'll be taking the alternative path, that is we will be considering the right child of this particular node. But before we build or expand the right child of this particular node, we will have to again compute the upper bound if we expand in this particular direction. So x1 is equal to 1, we have already done that. So x2 is taken as 0. Okay, and what would be the greedy solution to this particular partial problem? It would be 5 and 3 is equal to 8. So we will take this third item as a whole, and this fills up the knapsack, and the x4 would be equal to 0. So the upper bound would be 14 plus 6, which is equal to 20, and the highest profit so far is 14, and 20 is greater than 14, so it satisfies the requirement that the upper bound has to be greater than the highest profit so far in order to allow us to expand the child or the right child of the current node. So we'll expand the right child of the current node. So x2 is taken as 0, the highest profit so far is 14, and the knapsack has not been added with any other item, so it still remains 5. So now our active node is this node, and we will have to create its left child without computing the upper bound, because as I said, for the left child the upper bound will remain the same for any particular node. So we create its left child, which basically means item number 3 is taken as a whole. Okay, now this was only possible because the weight of item number 3 plus the weight so far in the knapsack is equal or less than or equal to m. So that is why we were able to continue with this particular direction, and up to this point the knapsack is full. Okay, so the current weight has changed here, as you can see on the screen, to 8. Okay, and the highest profit so far is now 20. Okay, now at this particular point of time we cannot add any more items to the knapsack, so the left child of this particular current node, which is this node here, cannot be generated. So we will it will be treated as null. However, whether we can expand the right child of this current node or not, as you can see on the screen, we have already done that, depends on whether the upper bound is greater than or equal to the highest profit so far. So if you see on the screen here, the path that we are at this particular point here, the first item has been considered, the second item has not been considered, the third item has been considered, and the greedy solution, as I said, the greedy method would give 0 to the final item. So this is the solution that will be given by the greedy method, and the total profit or the upper bound is 20, which is equal to the highest profit so far. Okay, so we can simply consider expanding this right child, and we have already done that here, and x4 will be taken as 0, and the profit so far is 20. Now obviously we have already exhausted our knapsack here as well as the items, so this is one of the solutions or that we can consider. So the solution vector in this case is x1 is equal to 1, x2 is equal to 0, x3 is equal to 1, and x4 is equal to 0. Now we have not yet finished with finding the solution to this particular problem, because there are still certain children which we have not yet expanded, and there is a possibility that they might yield us a higher profit. For example, the right child of this particular node, similarly the right child of this particular node have not yet been expanded. So that's what we will be doing so far. before we compute or determine whether we want to expand this right child of this particular node here, we have to compute the upper bound that can be obtained by expanding this. So in this case, at this particular point, we have considered item number 1, we have not considered item number 2. Similarly, going towards right, we are not considering item number 3 as well. The greedy solution would give 1 for x4 in this case, considering that we are here. x1 is 1, x2 is 0, and x3 is being considered as 0 because it's a right child. Right child here means not taking the item to the knapsack. So the best profit that can be obtained following this path is by taking 1 or x4 equal to 1. So the total weight would be 5 plus 2, which is less than or equal to 8 in our problem, as I talked about earlier, and the total profit would be 15. Now this 15 here, or the upper bound 15, is way less than the highest profit that we have so far obtained, because it was at this particular node that we obtained the highest possible profit. So it would be useless to expand this node in this direction. So we'd simply discard that. Okay, so we have killed this node. So the last remaining node is the right child of the root that we have to consider. So it means that we are considering 0 for the first node if we are moving in the right direction towards the right of this particular root node. Using the greedy method, we would see that it will yield x2 is equal to 1, x3 is equal to 1, and x4 equal to 1 by 2 in order to fill the knapsack. And the best profit that we can obtain is if we expand this node is 16.5. So that is the upper bound for following this particular path here. Again, this value is way less than the highest profit that we have obtained so far. So again, following this path would be fruitless. So we'll simply discard this node as well. As you can see, we have already found our solution. We have exhausted all the paths, and we have already found our solution, which was 20, which is the highest profit that is obtained. And the solution vector is x1 is equal to 1, x2 is equal to 0, x3 is equal to 1, and x4 is equal to 0, and we can display that. Now, in order to design our algorithm for this 0-1 knapsack optimization problem using backtracking, we will simply consider all the factors that we have discussed in this particular problem. And the first sub function that we will design is the upper bound function, which helps us compute the upper bound for a given k. So if we are at particular node k, so we will have to consider all nodes k plus 1 to n, okay, and try to find the upper bound that can be obtained. So we will first see how do we compute the upper bound for item k. So this is the pseudocode that basically computes the upper bound, that helps us compute the upper bound for a particular node k. So it has 3 parameters: the current profit, the profit so far that we have obtained, the current weight, so the weight that has already been added to the knapsack, and k, the item number that has already been added, up to which the decisions have already been made whether the item is added or not added to the knapsack. So these are the 3 parameters, and we are also considering m to be a global variable, which is the size of the knapsack, okay, and k is the index of the last item that has been removed. Removed basically means that we have considered whether the item needs to be added to the knapsack or not. So we use some temporary variables here. B stores the current profit, C stores the current weight, and we iterate from k plus 1 to n. So for all the remaining items for which we have to take decision as to how much of that particular item needs to be added to the knapsack, in fact whether or not that item needs to be added to the knapsack optimization problem. So for all those items, we add for I equal to k plus 1. This is basically the greedy method that we are implementing here. So the current weight, which we already saved in C, plus the weight of the item, k plus 1th item. So we save it in C. Now if this weight is less than m, so we have not yet filled the knapsack, we'll simply add the profit of this particular item to the current profit and save it in B. Okay, so if adding the next item does not fill the knapsack, okay, we will simply consider adding that item to the knapsack. So we add the weight to the current weight as well as add the profit of that particular item to the current profit. However, if it is either equal to or greater than the value of m, okay, if we consider this condition, if the current weight is less than m. So, if we have not yet completely filled the knapsack, then we will continue adding the profit and the weight of the current item. So, k plus 1th item. If the total weight by adding this item is equal to or greater than the capacity of the knapsack, then we will return last weight plus the fraction of the weight that can be taken for this current item I. So, this basically computes the fraction of the weight that can be taken for the current item I. It will give a value between 0 and 1. Finally, iterates for all the items. So, let us suppose if the knapsack is not full while we iterate all the items, all the remaining items, then the same value, the sum that is obtained by adding all the profits to this variable b will be returned. So, at the end of the day, this particular function returns total profit that can be gained if we expand from k plus 1 to n. So, this is the function which will give us the upper bound, and we will use this function in our backtracking solution to the 0-1 knapsack problem, which is given in the next slide. As you can see, we refer to this algorithm as BNAP, that is the backtracking knapsack. K here is the item number for which we want to call this function. So, initially this BNAP will be called as BKNAP of 1, 0, 0. I'll just illustrate of what this basically means. It has 3 parameters, this function, as you can see. The first one is the item number for which we are calling this function. Initially it will be from item number 1 onwards. CP here is the current profit. Initially we will have the current profit would be 0, or we can set it to -1 as well. And the current weight, that is the weight that has been added to the knapsack. So, initially it again will be 0. So, we can call this function for the at the start as BNAP of 1, 0, 0, or BNAP of 1, -1, 0. This function assumes that the weights are available in this array, which is a global array, and the profits are in this particular array P array, which is also a global array. Similarly, FW is the final weight, wherein we will save the final weight. Initially it will be equal to 0. Similarly, the final profit FP here is the variable wherein we will store that final profit, whose value is again initially equal to -1. I'll like to correct my earlier statement where I said that CP could be taken as -1. We cannot take CP as -1, we have to take it as 0. So, the call would be BNAP of 1, 0 and 0. That is how we will call this function initially. Okay. However, this final profit is initially taken as -1. So, we will see how this function works out. At the start, when we enter this particular function, we will simply generate the left child without checking the upper bound. The reason for this is, as said earlier, the left child will have the same upper bound for its parent. For example, we are deciding for k plus 1th item, okay, and if we want that k plus 1th item to be included, so xk plus 1 is equal to 1. For that particular item, the upper bound will be the same as was for xk, or the kth item. So, for the left child, we will not be testing the bounds. However, we need to see whether a left child is feasible, as was illustrated in the example. So, the current weight that we have plus the weight of the item that we are considering right now, if it is less than or equal to m, only then can we build our left child. If it is not possible, then this particular left child is simply killed, or we point it to a null value. So, if this is satisfied, if adding the current item to the knapsack does not overfill it, then we can continue. We will save the temporary string in this y here. So, yk is equal to 1. So, means kth item is being considered. Now, if k is less than n, it means we have not exhausted all the items here. Then we will have to using recursion make another call to BNAP for the next item. So, BNAP of k plus 1, which is the next item. However, at this point the current profit would be incremented by profit of the item that was just added, this statement. So, we will have to make another call to same function for the next item, that is k plus 1th item. However, the profits now and the current weight and the current profit will be modified. We will add the item's weight that we just wanted to add to solution to the current profit. So, current profit, that is so far, plus profit of the kth item. Similarly, the current weight would be added with the weight of the currently added item. So, this call will be again made, and this the tests will follow. When we return from this particular call, whether the left child or right child was not, let us suppose, created, or it was created and both the children left as well as the right child was created by this particular function and returned a value, we will have to check whether the current profit plus the profit that we just added, okay, is greater than the final profit. As I said, final profit here was initially started from -1. So, we will keep on changing this. So, if the current profit plus the profit that is obtained from by adding this current item is greater than the final profit that we have stored so far, the best possible profit, and also k is equal to n. So, if we have we are considering the last item, then obviously we have found one of our solutions. So, the final profit is equal to the profit that is obtained by adding this item to the solution. Similarly, the final weight would be the current weight plus the weight of the item that is currently being added to the solution or the knapsack, and we simply display it here. So, this y was a temporary vector which stored the values for the solution temporarily, and we move those values to this x here, which is the final vector when our solution has to be stored. For the case of the left child, so when we are considering an item, now whether or not we need to build or expand the right child of the current node or not, as was illustrated in the example, we need to check whether the upper bound or the best solution that can be obtained by expanding this right child is greater than or equal to the best solution so far. So, the best solution so far is saved in this FP here, final profit. So, we will make use of the U bound function that we just discussed earlier. In the previous slide, we discussed the U bound function. So, this U bound function is called here for the current profit, current weight, and kth item. Now, if it returns a value greater than or equal to the best known profit so far, okay, again that is what the bounding function was all about, as we discussed earlier. If it is greater than the best profit so far, then we will expand and create the right child and search for the solution using that. So, yk here is equal to 0. As I said, the left child for a node means that the next node is being considered, and the right child for the current node means that the next item is not being considered. Okay. So, the right child here means yk would be equal to 0. So, we are not considering the kth item. Again, if we have not exhausted all the items in this case, if there are still certain items left, then we obviously need to make another call to the bnap function, okay, with for the next item, considering no change to the current profit and no change to the current weight, because we have not considered the kth item, as you can see. So, the kth item is not considered. So, the new call to bnap would be for the next item with unmodified profit and unmodified weight for the current node. So, once we get back from the call, if the current profit is greater than the final profit and this k is equal to n. So, final profit is taken to be the current profit, and the final weight is taken to be the current weight, and for I equal to 1 to k, we transfer the values of y to x. So, as I said, y here is a temporary vector storing the intermediate values of our solution tuple, and this x here will be the final solution in our case. So, this you can work out on the previous example, see by making calls by passing those arrays. As I already said, you can set w and p equal to the values which were earlier shown on the slides, and take f final weight initially equal to 0, final profit equal to -1, and then try to dry run this code on the earlier example, and hopefully you will be able to get the idea of how basically it works. So, with this particular lecture, we have ended our discussion on the backtracking problem. Although this is the backtracking solutions are not limited to only the examples that we have discussed here. You can explore other examples, other optimization and combinatorial problems, work on those problems using the techniques that have been discussed in the past couple of lectures, and see how you perform on those examples. So, we are left with one more algorithmic technique that we have to discuss, and it is the branch and bound technique, which we will be discussing in the next couple of lectures. And till then, thank you.